So in case you have not collected your quiz, it is there. For the Zoom people, if you want to collect your quiz, you have to come here. All right. So we have actually completed the discussion of Markov chains. There's still a lot in that chapter that we can talk about, like dynamic programming. I actually thought whether I should talk about it, but I think I want to talk more about estimation theory, which comes after these two lectures on detection theory. So I decided not to talk about dynamic programming there. Okay, so for the next two lectures, we will talk about detection and hypothesis testing. And this is the material in chapter 8 of the book. So you should read chapter 8, all right? And then in the last two lectures, we will talk about estimation theory. And the notes have already been prepared. We will not be using the book. And I prepared my own notes. So you may wonder, I say these two lectures, right? Next week is public holiday. So we will not be here, but I will do the lecture over Zoom. Okay? So it will not be as long as 3 hours, but it will be something because I cannot finish talking about hypothesis testing today. Okay, so basically we will have a lecture next week, but we will not be here. I will just be doing it from my office, for example, maybe. Okay, so this is chapter 8, and the content is on detection and hypothesis testing. And I don't think this is very difficult, but there are some tricky aspects. Okay, so can the Zoom people hear me? Okay, great. Okay, so what is detection and hypothesis testing? Okay, this is a very classical topic, but I hope that everyone knows this because it's very useful in statistics. So there is a model, and each model represents the state of the world. And it is characterized by a discrete random variable. By a discrete random variable. And in this chapter, we will use X to denote a hypothesis. Okay, this is known as the hypothesis. So in many other books, they will call hypothesis as H. All right, but here, just to be consistent with the book, I will use X. So X is a discrete random variable. Now, discrete random variable can have finitely many values, can take on finitely many values or countably many values. But in our discussion, it will always be finitely many values. Okay. Now, so this state of the world is something that we want to infer. We want to infer whether or not there is a maybe a malignant tumor in a particular patient. We want to be able to understand whether or not what we see in the sky is a meteor or it's something else, something else strange, a UFO. So we want to be able to say something about the state of the world and to make a guess about what it is, but we cannot guess it without having some observations. So the observations Y can be discrete or continuous. Okay, so Y and X are correlated random variables. Okay, if they are not correlated random variables, then you cannot use Y to say anything about X. So the whole point of this chapter is to use Y to say something meaningful about X. Okay, so the picture is as follows. We have X that takes on values, finitely many values, and we will say that it takes on M values, and we cannot see what X is, but rather we can observe it through Y. So these are our observations. Okay, and we want to design this thing here. This is called a detector. That's why this whole topic is called detection. Detector that will give us an estimate of Y. And this is a number between 1 to M minus 1. Okay, so basically we want to design, the whole job is to design this particular function X that brings us from the domain Y. So Y here belongs to script Y. To, we want to design this detector. Sometimes in information theory that I work on, it's called decoder. Okay, So x hat is basically a function that brings us from y all the way to 1 to m minus 1. Okay, we want to design this function so as to maximize the probability of correct decoding. And what is the meaning of correct decoding? The decision that we make is correct if x hat of y is equal to x. All right, so capital X is the original, the true hypothesis that we do not know, and we observe it through y, and we want to design x hat that takes in y, the observations, and gives you a particular number between 0 and m minus 1, and we want to compare that to the underlying hypothesis x. It is that simple. Okay, so now because x here is modeled as a random variable, it has a so-called prior probability, has a prior distribution, if you wish. Distribution. Okay, this is the so-called Bayesian setting where x has a distribution. So we denote it by p of x of x. This x here is uppercase, this is lowercase. This is probability that x is equal to little x, and here x can take on values 0 to m minus 1 only. Okay, so this is the probability of x. Sometimes we abbreviate this as p of x even. Okay, so this is called the prior distribution or the prior, and we have a likelihood model, likelihood or observation model, which is given by p of y given x, which is this object here. So p of y given x is this so-called observation model. In information theory, we call this a channel, if you wish. So p of y given x, this is our observation. This is the underlying true hypothesis. Is the probability of y being equal to y condition on x equals to x in the discrete case. Okay, for discrete y observations. And sometimes we write this as f of y given y, y given x. This is a density, all right, for continuous observation y. And I have to let this friend in. Okay, so that this object here, this distribution here, characterizes what sort of observations we get conditioned on the fact that the true hypothesis is little x. Okay, so the whole purpose of these couple of lectures is to understand how well we can do in terms of estimating x from y. This is a super fundamental problem, as you can imagine, right? So I want to send you a message, but unlike in this lecture theater, if we go to the engineering canteen, it is very noisy at lunchtime. So you may get some distorted version of my message. So you, in your mind, you want to design a decoder to decode my message. So how well can you actually do? This is a super fundamental problem, right? So we have to study this. So one way to go about this is through the so-called MAP criterion. MAP is short for maximum a posteriori. MAP criterion. Okay, so this is what we'll discuss now. Okay, so we will assume that y is continuous in this discussion, but the whole thing goes through verbatim if y is discrete. Assume y is a continuous random variable. So if f of y is greater than 0, this allows us to define p of x given y, x given y. This is nothing but base rule, f of y given x divided by the bottom, which is f y y, okay, where the bottom f of y is nothing but by the law of total probability p of x. Let me make this clear. P of x, x prime, f of y given x, y given x prime. Here x prime runs from 0 to m minus 1. So this is a base rule, it's nothing special. All right. So this is just writing down what is base rule. We want to maximize the probability of choosing the correct hypothesis. And here is a small little fact. To maximize, and it's at first glance, right, this is not so obvious. Okay. To maximize the probability of choosing the right hypothesis, and we will make this precise in a moment. Hypothesis Okay, we have to choose our decoder or detector to be given by the following rule, to be x hat y. So a detector or decoder is nothing but a function that brings you from the y space to the x space. Argmax over all possible x belonging to 0, 1, m minus 1 of the p of x, y, x given y. This is known as the map rule. This is the maximum a posteriori probability rule. Okay. So we want to maximize the probability of choosing the right hypothesis. And the rule that I prescribed to you is the map rule. Okay. So a few words about this. One is that you see here, this p of x given y, this has a name. Okay. Let me repeat the name. So this guy here, p of x is called a prior. I've already talked about this just now, right? Now, this is called the observation model or the likelihood model. Okay, and this is known as the posterior probability or posterior distribution. Okay, this thing at the bottom here also has a name. It's called the model evidence. This is all Bayesian inference things. Okay, so why are all these terms the way they are? This is the prior probability. Prior in English means before. Before you observe the observations y, your only information about x is through this particular distribution. You have no other information about x. So the best you can do maybe is to select the argmax of p of x. That minimizes your probability of error. That requires a moment of thought. Okay, but this before anything happens, before you see any observations. This is your best guess, to rely on px only. Now, the likelihood model is captured by f of y given x. That is how likely you see y given that the underlying state of the world is x. Now, this guy here is a product essentially of the prior and the likelihood. So you are merging what you knew beforehand, p of x, your prior belief, together with your observation model to form your post or posterior belief about the state of the world. See, this is your state of the world, p of x, your belief about x, condition that you know y is equal to y. Okay, so this posterior in English means behind. Okay, or after the fact, after you have observed some observations. And this guy here is required for normalization. And this guy here is super important in the context of model selection in machine learning. Okay, so these sort of things can have meanings. It's called model evidence or Bayesian score. Okay, so in my other class, I talked a lot about these things also. All right, so this is the map rule. So let's try to prove that this actually maximizes the probability of choosing the right hypothesis. Okay, so another way to write this is that the map rule xmap. So this is a particular function. I'll index it by xmap is argmax of x, p of x, which we will abbreviate to px very soon, f of y given x, y given x. So this guy here is equivalent, this guy here is equivalent to the above. Why is that so? These two guys are equivalent. Because here we are taking argmax over x, all right? And the bottom here has nothing to do with x. So we can just throw it away. So maximizing this guy here is the same as maximizing this guy here. So this guy here is this guy here. This product here is this guy here. So we will work with the second expression because it is marginally easier, but everything is the same. Okay. So this is just a small little comment proof. Okay. So we want to show the following. Let XA, Y be any other decision rule. We want to show that it does not perform better. Okay, we want to show that it does not perform better than Xmac. I'm not saying that it performs better. It performs strictly worse. Okay, but it cannot perform better. So we must say things the right way. Let be any other decision rule captured by this A. All right, just some simple index. Then it is true that if we just follow through the definitions, x hat map y condition on y is bigger than or equal to p of x given y, x hat a y given y for every y in y. So why is that so? All right, this looks a bit complicated, but it's not. Right? This comes, and we have a friend joining us. So this comes from the fact that x hat. Okay, maybe I will make this super precise. So let's make it x map also. Why? This because x map y maximizes this, okay, or equivalently this. So this must be at least as large as that because it is argmax. That's the meaning of argmax, right? This is any alternative estimator or detector or decoder. So it must perform no better in this sense. We are just tracking the definition of argmax. Now, so what we can do now is to integrate over all possible fy. Why can we do this? Because fy is non-negative. Okay, x map y condition on y hat dy bigger than or equal to integrate f of y, this guy here, and dy. Okay. All right. So what do we have here? Note that the left-hand side can be simplified slightly. Okay. The left-hand side is the following. It is nothing but sum over all possible values of x of fy y, p of x given y, x given y, indicator of x map y equals x. Okay, dy. All right, so I have done a lot more than prescribed. Okay, so let me adjust this a little so as to make it clearer. So I put the fyy outside and sum over x here. Okay, the claim is that this part here that I'm coloring now is the same as this part here. This is nothing but definition. All right, I'm summing over all possible values of x, but this indicator only turns on to 1 if these two coincide. And this is just a trick, right? Because if these two coincide, then my x takes on the value x map. Okay, now if x map is not equal to x, this thing gets killed. So it's if these two red parts are equivalent. But this allows us to do something, all right? This allows us to swap, and then we can swap because all these are non-negative, all right? Sum over x, okay? So we can swap in the sense that, okay, let's do it slowly. So now we can do sum x. Now we have the joint, right? Basically, if you merge this guy and this guy, you have the joint distribution. So I'm going to skip one step and I'm going to just write down base rule, which is p of x, f of y given x, y given x. We will keep the indicator around because it looks nice. dy. So here we are using base rule by merging the two things in yellow. Okay, so the thing in yellow, the two things in yellow form this one here. Okay, so then this is just nothing but base rule. Now we can extract the stuff that we want, which is outside here, and we can integrate fy given x, y given x of this indicator, x map y equals to x dy. Okay, this is just rearrangement. But what do we notice here? Okay, this is nothing but sum over x, p of x. What is this inside here? It is nothing but the probability that x hat map capital Y is equal to little x, condition on x is equal to x. Maybe it's better to put capital X here. Okay, here what are we doing? What is the meaning of this? It looks a little bit daunting, but it's not. We are integrating this likelihood over this particular region of y's. So this is, you can think of this as the domain, a subset of y's that I'm integrating over. This is a subset, so I can put it here. All right, what does this mean? I'm capturing the event that x hat map y is exactly equal to x. when when x is equal to little x, because x is fixed to be x here. Okay. Now then we can write this. This can be captured into one form. X map y is equal to capital X as follows. Merge everything together by the law of total probability. Now you see that we have done this for X map. This is for the left hand side, but this does not depend on what is X map, right? So similarly, for the right hand side, we have the right hand side, basically this guy here. The right hand side, this guy here, can be written in a very similar way. This is the right hand side. This is the right hand side here. The right hand side, similar for the right hand side, we have that it equals to probability of any alternative decoder equals to capital X. Okay, so in summary, we have probability that X map of capital Y equals to X. It does, most of the time it does better, but it does not do worse than this guy here. And this holds true for any other hypothesis or for any other decoder. In summary, blah blah blah, for all decoders or detectors. A. Okay. So obviously, if A is equal to map, then obviously these two are the same, right? But A is something else, may not be the map. And in which case, the probability of correct detection is the probability that I guess the hypothesis correctly. All right, it will be strictly less than map. Okay. So now let's go through this argument one more time, and let's go through the fact one more time. Okay. So the idea is as follows, right? Oh, we have this friend. Okay. So the people in the Zoom, feel free to ask questions as well, okay? But now I'm going to go through this small little proof. Okay. So what are we claiming? We have the map rule. The map rule is this rule. Where's the map rule? The map rule is here in the red, okay? It says that, okay, now I know that there is the state of the world X that I would like to guess. I want to know whether the patient has cancer or not. I take a few measurements from the patient, and blood tests, urine tests, etc., and more detailed X-ray and so on and so forth. So that vector of observations constitutes my Y. Okay. Now, what is my best guess of whether or not the person has cancer? Is to do this map rule. Okay. Now, so the map rule says that you form your posterior distribution P of X given Y, X given Y, and you look for the X that. And you observe Y equals to little y. Okay, you observe that Y is equal to little y, and so you fix this already. Okay, so now you would like to find out what is the X that maximizes this probability. And this makes a lot of sense because there are only m values of X. So you can form m numbers and you see which one is the biggest. This is perfectly well defined. You don't need to do soup. So this is the map rule. Map rule is given by this. It's the same as this because the denominator does not matter. The model evidence does not matter. It matters in some other scenarios. Okay. So what is the statement? The statement is that the map rule is the best among all possible rules. Okay. And the proof is almost straightforward. It's a matter of bookkeeping. All right. So how do we show that I am better, or map rule is better than everybody else? Let me take somebody else. Let's call it XA. And it has some output, it has some decision. But based on the definition of the map rule, we have this relationship. X map is the largest, it maximizes the posterior probability over all possible A for every fixed Y. So now we can integrate both sides like this. So now we can perform a little bit of calculus gymnastics, but it's not too much, all right? So we can move things around, shift here and shift there, and apply Bayes' rule here. Okay, and we notice that the insight here is nothing but the probability of correct decoding, the probability of correct detection here, condition on X equals to X. Now merging this with the prior probability, we get the probability of correct decoding or detection. All right, and so similarly, this derivation makes no use of X map. We make use of X map through this inequality here, But the right-hand side here, the green part here can be controlled by this. It's exactly equal to this. And so in summary, X map does at least as well as any other rule. No other rule can beat X map. Is this clear? All right, this sort of simple proof, hopefully you understand. Okay. Any questions from the people in the Zoom? I don't think this lecture is so. Oh. Zheng Tian, X hat is the estimated value of X from Y. Yes, using the map rule. So it is not any arbitrary estimator. It is the estimated value of X given Y using the map rule, i.e. X, so hat of X, Y is equal to argmax X of P of X given Y, X given Y. So it is exactly this rule, okay, not any other rule. So what is the problem of the map rule? All right. In real life, we do not have any idea about this. These are model distributions or the likelihood model. So this is very hypothetical. In real life, who is to say that, okay, the probability that you will observe a bad blood test, whatever that means, if a person has cancer is 95%. So all these things we don't really know. So we have to use, for example, training data to learn this sort of thing, but that's a whole new different area. Okay. Suppose we know all these probability distributions, what is the best we can do? Okay. Zheng Tian, is it clear? Okay, good. So now let us move on to the binary case in which we can see more stuff. Okay. All right. So this is not very difficult. It's a matter of bookkeeping. Binary map detection. So in this case here, m is equal to 2, and you can take the x to take on two values 0 and 1. Okay. So we always assume that the prior distributions are all positive, otherwise there's nothing to do. Very hard to talk with that. So P of x of 0 is equal to, say, P0, and P of x of 1 is equal to P1. Okay. So now our model evidence, f of y is equal to, then this is just tracking the definition, y given 0 plus P1 f of y given x, y given 1. Okay. So we can also write down the posterior probability. By the way, this is, as I mentioned just now, it's called the model evidence. And it's very useful for model selection in other contexts. And there's a lot we can say here. The posterior probability of x given y, okay, where x takes on the value, say L can only take on two values because x can only take on two values. It can be written as P of L, okay, L takes on x, L is x big, f of y given x, y given L, divided by f of y of 1. So what is the map rule now? What is the map rule? All this stuff that I've written above is just for preparation purposes. What's the map rule? The map rule says that we should choose argmax, right? We should choose argmax of map rule says we should choose the argmax over L of this guy here on top, basically the posterior probability. So we can write this out for the binary case very simply. Okay. So let us take this guy here, over here, and do some comparisons. Okay. So we have this, and say that L, let me instantiate L to be equal to 1 here, and greater than, less than, and this is a very strange symbol that I will explain in a moment. Okay, X can only take on two values, 0 or 1. Okay, so if this guy here is bigger than this guy, then the argmax is 1. Okay, don't ask me what happens at equality. Okay, say it never happens. Then here, X hat map, you will declare is equal to 1. Now, and when I put the X map above like this, I really mean that it goes with this symbol here. Okay. On the other hand, if the symbol below is in effect, then x map y we take to be equal to 0. So that is this case here. Okay, so this is the notation that we use. Okay, we will put some clause above the greater than, we'll put some clause below the less than. But the way to read this is that if this is true, we'll make this decision. And this is true if this guy is bigger than this guy, in which case the map rule says that you should choose hypothesis 0. Okay, but you notice that this is actually too long-winded, and you can cancel the stuff at the bottom because it has got nothing to do with 0 or 1, right? Any questions here? Any questions from the Zoom people? How about Ma Zheng Tian? No? Okay. Okay, very good. So now we can actually simplify this, as you can see, and we can write this as f of x given y given 1, divided by f of y given x, y given 0. Compare this to P0 over P1, which we call eta. This eta is known as a threshold in the detection theory literature. And on top, what do we decide? We decide x hat map y equals to 1, below x hat map y equals to 0. Okay, so we compare this thing known as this is a very important name. I use this thing every day. It's called the likelihood ratio. Every paper of mine has likelihood ratio. Okay, this likelihood ratio, and this is given a very important symbol in the book, is called lambda y. Okay, so the whole point is that you have these two likelihood models, f of y given x is equal to 1, f of y given x is equal to 0. Okay, you can form their ratio, the likelihood ratio. And what are you comparing that against? You are comparing that against threshold. Now, if your thresholds are such that you have equal belief of the two states of the world, this person has 50% of my population has cancer, 50% of my population does not have cancer, then it's equal to 1. Then in fact, you're only comparing the likelihood ratio to 1. Okay, but if only 5% of the population has cancer, 95% of the population does not have cancer. So let's give this some numbers. So this will be no cancer is P0. P0 is called the null hypothesis actually. In statistics, null hypothesis means nothing happens. So 5% over 95%. So this is some small number, right? This is some very small number. So in order to declare that the person has cancer, you are actually comparing this likelihood ratio to this different number. It's not 1 anymore. And your evidence to say that someone has cancer must be very strong, because your prior probability of someone having cancer is actually very weak. Only 5% of people have cancer. Everyone else is quite healthy. So you need to compare this to the strength of your prior belief. That's why I say that this whole area is to merge your prior belief with your observations. How strong are your observations relative to your prior beliefs? Understand? Okay, this is just an example. I'll get rid of this. So this is called the likelihood ratio for, okay, this should be the same color. For a binary detection. Binary detection is also called binary hypothesis testing. Hypothesis testing problem. Okay, and the likelihood ratio is super important. And basically, the whole point here is that the optimal, I want to use the black. The optimal decision rule in the binary case is a threshold rule. Threshold rule of the likelihood ratio against the prior. Likelihood ratio and the threshold is given by the ratio of the prior probabilities P0 over P1. Okay, so this threshold rule is super important because it's easy to implement if we know the models, if we know the likelihood model f of y given x. Okay, I've already alluded to this, and this is maximum likelihood estimation that we'll talk about next. But before this, does anyone have any questions about the binary case? I think it's not difficult, it's quite straightforward. Does anyone at home have any questions about the binary case? So in the binary case, we are just basically comparing this likelihood ratio to a particular threshold. Where does it come from? It comes from the map rule. The map rule is this rule here, where we are comparing the posterior probability, and the evidence gets killed. You have the threshold that's formed from the ratio of the prior probabilities, and this left-hand side is nothing but the likelihood ratio that's given this symbol lambda y. Any questions from the Zoom people? Okay, if not, we can move on to a special case, which is the maximum likelihood case. So maximum likelihood is the simplest scenario. And there's a lot we can say about maximum likelihood, but we won't have time. Maximum likelihood can actually take up 13 weeks. We can talk a lot about the various properties of maximum likelihood. In maximum likelihood, the priors are uniform. And so the threshold is equal to 1. And so this simplifies our test to a test of the likelihood ratios. Likelihood ratio comparing the likelihood ratio to 1. Okay, so here we have x hat. Very soon I'll drop the map. Okay, it's very hard to write this map here. Equals to 0. Okay, so there are no more priors, and in effect, this is the same as lambda y comparing it to 1. Okay, here is 1 and here is 0. By this sort of things, right? This sort of symbol here. Okay, I mean, this means decide 1. Decide in favor of hypothesis 1. Okay, so this quotes here, this is very old-fashioned, but it says decide in favor of 1. All right, so now in detection theory, okay, this is a detection theory, very classical literature. There are 2 types of errors, at least in the binary case. 2 types of errors. Okay, 2 types of errors we want to control, right? One type of error is called type 1 error. The other type is called type 2 error. Type 1 error, type 2 error, these terminologies are used in statistics. They are kind of confusing. There are other terminologies like probability of false alarm and probability of misdetection. There's recall precision. They all mean roughly the same thing. Okay, so it's very hard to remember. So I'm going to tell you what is necessary for this class. Okay, but let me just first write down the overall probability of error. Then we will talk about the individual errors. Okay, so the overall probability of error, we write it as E eta. Eta actually is nothing but the threshold. Okay, so the prior probabilities may or may not be half. So now we have departed away from the maximum likelihood discussion. Okay, so now basically what we want to do is we want to look at the overall probability of error. Okay, and this is the threshold. It does not have to be 1. Need not be 1. Okay, we may not be in the maximum likelihood scenario. Now, by base rule is nothing but, let me just make this clear, probability of x being equal to 0, probability of making an error, x equals to 0, plus probability of x is equal to 1, probability of making an error conditional on the fact that x equals to 1. Okay, so this can be written as P0 and P1. Okay, so these things have names, and let me talk about this maybe now. So usually in statistics, it's called the null hypothesis, and this is called the alternative hypothesis. Okay, so these are some statistics terminologies. So here, probability of you making an error conditional on the fact that x is equal to 0. What does this mean in real life? Okay, so x equal to 0 is a null hypothesis, means that everything is normal, right? So the person does not have cancer. So what are you trying to say here? This probability is that you are saying that, for example, the probability of a patient, you declare that the patient has cancer. This is the declaration, decide, right? Because this is decide, this notation is decide. Patient has cancer when the ground truth is he or she, maybe I use she, right? She does not have cancer. So this event has a name actually. It's called false alarm. Right? Because the person does not have cancer, but you say the person has cancer. Okay? Usually false alarm is not so serious. False alarm we can control by 5%. Okay, the next one is super serious. E eta makes you make an error condition on the fact that x is equal to 1. What is the meaning here? Probability that you declare that the patient does not have cancer, when in fact she has cancer. All right. So this event here has a name. It's called misdetection. This is very serious, and this is the sort of thing that we want to really minimize. Okay. So misdetection is a very serious thing because okay, this guy, this woman here, she has cancer. She has cancer, but you say that she doesn't have cancer. So if you don't treat her, she's going to die. So this is very serious, and this is what we want to control. So as you can see in this medical example that I have here, these two errors are not symmetric in real life. They need not be symmetric in real life. So, well, whatever it happens here, okay, we have these two errors. This is also called, okay, this is also called type 1 error in statistics, I believe. I don't know, I cannot remember precision and recall, sorry. This is called type 2 error. Okay, right. So I can remember type 1, type 2 because this always appears in my works. Okay, so we want to control these, right? And we will have talked a lot about controlling these two objects a lot in the next, like in this lecture and the next. So in this Bayesian setting, this Bayesian, because we have prior x as a prior, we would like to control the average probability of error. This, by the way, is called overall average probability of error because we are averaging over the prior here. Okay, so in fact, whatever hypothesis test we are doing, we are always partitioning the sample space into two portions, into two disjoint parts. Okay, and for example, using the map rule, how are we partitioning the sample space? All right, we are partitioning it in this way. A0 is equal to the set of all possible y's for which my likelihood ratio is less than eta. Okay, so in this case here, do I declare 1 or 0? Okay, so I have this. Okay, using the map rule, if I'm less than eta, I declare 0. Okay, that's why this is the 0 region. A0 is a 0 region, and A1 is of course the complement. Lambda y is bigger than or equal to eta. So the idea here is, okay, so this corresponds to making the map decision equals to 0, and this corresponds to making the map decision equals to 1. The picture you want to have in mind is the following. So this is your entire sample space. All right, this is all possible y's that you can observe. Now, here is A and here is A0, A1 here. So if your observation lands inside here, so if your observation lands here, then you will decide in favor of hypothesis x equals to 0. And if your observation lands instead here, then of course you will declare x equals to 1. So you partition the sample space. Okay, so there's no overlap between A0 and A1 because at the same time you cannot say that two hypotheses are true. Now, if we can say that, then we can do a lot of other interesting mathematics that I do. This is called least decoding. All right. So what is the probability? What is the probability of this? Is called false alarm because the state of the world is you don't have cancer, but someone says that you have. This is called false alarm. So actually, what's happening is that the true distribution is given 0. Okay, the true distribution is conditioned on x equals to 0. But what are we integrating over? We are integrating over the region A1 because we are deciding in favor of x equals to 1. So basically, our y landed in this region here, but in fact, the y was generated from this distribution conditioned on 0. Understand? So this is the probability of false alarm. Okay. So similarly, the probability of misdetection is given by the following. Integrate over A0. This is very serious. dy, and here we are integrating over this particular distribution y given 1. The state of the world is that this person has cancer, but you said no. Okay, so this is the probability of misdetection. Okay, so all these things can be written in another way. All right, for a particular for our likelihood ratio test for the likelihood ratio. By the way, this is called likelihood ratio test. Okay, this is called likelihood ratio test because we are testing the likelihood against a certain threshold. Okay, so this can be written as lambda capital Y bigger than or equal to eta condition x equals to 0, and this is probability lambda y less than eta given x equals to 0. Why is this so? We are integrating over A1, A0, and A1 is this region here. Okay, is this region where this is very ugly. Is this region here where the likelihood ratio is bigger than eta? So we are integrating over this region. That's A1, and that corresponds to exactly this event here. Likelihood ratio bigger than eta. We need to put capital Y here because this is a random variable. It's inside the probability. Okay, but the state of the world is x equals to 0. Okay, so similarly, A0 is given by this particular set here. It's given by this particular set. So we are integrating over the same set here when we are talking about the probability of misdetection, which is condition of x equals to, I'm sorry, this should be 1. No one corrected me. Okay, this is the probability of misdetection. Okay, we can express this all this in terms of likelihood ratio. Okay, so this is A0 here. Now, so you notice that the following remark holds true, and that will motivate our discussion of sufficient statistics. Okay, but before this, are there any quick questions on this topic here, which is on evaluation of different error probabilities? Okay, any questions from the Zoom people? Later on, I will do some concrete examples that will make things very clear. Any questions from the Zoom people? How many friends do we have here? 19 minus 2. Okay. All right. So if not, let me go on to sufficient statistics and the remark that I want to write down. This sufficient statistics is very deep. Okay. We use it at least I use it all the time. Okay. Right. The idea is as follows: if the one-dimensional quantity lambda y can be found, then we can perform a threshold test on it. A threshold test on it without further reference to y. Okay, what is the implication here? Now, y represents your observations. It could represent, okay, so the patient either has cancer or no cancer. You take 1,000 measurements from the patient. You are very careful doctor. You take 1,000 measurements. Okay, now you want to process this 1,000 measurements. This remark says that you don't really have to, if you are able to form the likelihood ratio. The likelihood ratio, output of the likelihood ratio is a single number. The optimal thing to do is to form the likelihood ratio, which is a function of this 1,000 measurements that you have taken. So the 1,000 measurements could be captured in this y here. Apply your function. Okay, you apply your function lambda to the 1,000 measurements, you get a single number. And the optimal thing to do is to compare this single number to eta, a single threshold. So this is a significant so-called dimensionality reduction. We initially had a lot of features or a lot of different variables that we collected, but then we don't really care about what they are as long as we can construct this one-dimensional quantity, the likelihood ratio, and it's optimal, as we have proved just now. Okay, a bit unbelievable, but let's discuss it a little bit more. Okay, for example, there are two hypotheses, okay, in the world. Either this coin, so we have this coin here. Let me digress. This coin, this is my coin, and we know that its bias is either 3/4. This is my exam question a few years ago. Its bias is either 3/4 or 1/4. So we toss the coin, n equals to 100 times. Okay, so we observe y1 up to y100. So we observe 100 numbers, 0, 1, head, tail, whatever. Do we need to care about the order of the heads and tails that come out? No. All we have to collect is the total number of heads, the total number of tails. That forms a sufficient statistic. Why? This requires a proof. Right? But it's intuitive that if you want to decide whether the coin has bias 3/4 or 1/4, you don't need to see the exact sequence y1 to y100. You just need to see the proportion of heads and tails in this sequence y1 to 100. Right? So we don't have to keep the vector of length 100 around. We just have to form a single so-called sufficient statistic. And that motivates the topic of the next discussion. Okay? So this is a little bit deep, and let's talk about the notion of sufficient statistics. This is a very important, very deep thing. Okay, definition. For binary hypothesis testing, sorry, I'm very lazy already. Let me write PhD. Sufficient statistic, and I will provide some examples, is any function v of y of the observation y for which the likelihood ratio can be computed. Lambda y can be computed. Okay, so what does this mean? Okay, in other words, v of y is a sufficient statistic of y if there exists another function u of v such that lambda y is equal to u v y for all y. There's a lot of symbols here, and you may be confused, but I'm not confused. All right, lambda y is our likelihood ratio. Okay, it's our likelihood ratio. Now, a sufficient statistic is any function v of y that has the certain property that if you use v, if you have v, you can construct the likelihood ratio lambda y. Okay, now this v may be very much lower dimensional than y. Y here may be a vector. V here may be much shorter than a vector, but it may still be a sufficient statistic in the sense that you can reconstruct lambda y given vy. And what is the meaning of can reconstruct lambda y given vy? It means that there exists a, okay, you cannot see it, but there exists a function that whose domain is v, such that you can reconstruct lambda y. So if you put vy into u, you can recover lambda y. Okay, so this is too abstract. Let me give you some examples. Okay, this is a trivial example. Example. Okay, vy is equal to log of lambda y is this is a trivial one. Sufficient statistic for binary hypothesis testing. Why? Obviously, right? Because there certainly exists a function u of v, which is e to the u v, that can help us reverse the operation. U of v, this is a function, helps us to get from the v space to lambda, because u of v of y is equal to e of ln of lambda y, which will help us to recover lambda y. But it's a trivial example because, okay, if I take any invertible function of lambda y, then I can go backwards to lambda y. Okay, but this is too trivial, so let me give you a more interesting example. Okay, so does anyone have any questions on this? Okay, so this example is a very classical example, but we'll look at something more complicated later on. Detection of antipodal signals in Gaussian noise. Signals in Gaussian noise. Okay, so the idea is as follows: y is equal to x plus z. All right, and x is taking on only two values, minus b and b. Okay, minus b corresponds to hypothesis 0. Okay, and plus b represents hypothesis 1. We're not going to say that. All right, and here z is distributed as Gaussian with certain variance. Okay, so we can write down what are. So notice that now my y, right? My y here is infinite value. Okay, it's a real number, but we want to come up with a certain sufficient statistic. It's a single number such that we can compare to a threshold and we can make a good decision. Okay, so now let me write down f of y given x, y given b. Okay, so we can write down this y given the event that x is equal to b is nothing but distributed as Gaussian with mean b and variance sigma squared, and y condition on the fact that x is equal to minus b is distributed as Gaussian with mean minus b and variance sigma squared, right? So now we can write down f of y given x, y given b carefully. And this is nothing but 1 over square root 2 pi sigma squared e to the minus y minus b, this Gaussian thing, right? 2 sigma squared. Okay, so this is the case for the hypothesis x is equal to b. And to save my writing, we can copy and paste here. And now for the case where x is equal to minus b, we have plus here. Okay, so we can now form the likelihood ratio, which is lambda y, is f of y. Usually we put the hypothesis 1 on top as a matter of convention. Okay, and hypothesis 0 at the bottom. Now, we notice first and foremost that all these things cancel. All right, this prefactor cancels. And then if you expand these sort of things here, right? If you expand this part here, you see that the first term and the last term cancel. If the first term and the last term are quadratic, the y squared and the b squared cancel, and you only have the cross term left. So I am not going to do all this algebra, because if I do all this algebra, I will make a mistake. So I will just write down that the cross term remains, okay, and the cross term is how many? There will be a factor of 2yb over sigma squared. Okay, this is all algebra. So the optimal detector, optimal test, is the following. Okay, you take the likelihood ratio and you compare that to eta, which is defined as p0 over p1. Now p0 is the probability that x is equal to minus b. P1 is the probability that x is equal to plus b. So here we make the decision that x hat is equal to b, I believe. Yeah. Here you make the decision x hat y is equal to minus b. Okay. So usually we are dealing with distributions that are exponential families. All right. We like to deal with distributions that are exponential families in the sense that they are e to something. Most distributions are like that. It's very difficult to think of some distribution that's not in exponential family. Okay, so if we find it convenient to take the logarithm now. Okay, so now we can form what is called the LLR of y. that is nothing but the log of lambda y. So we recover 2yb over sigma squared. And we are going to compare that to ln eta. Okay, we just take log everywhere. And we see that the optimal decision is y, compare y to sigma squared log eta over 2, I think. 2b, yeah, 2b. Okay, and we take the positive decision on top. X hat y is equal to b. Okay, so as you can see here, right, this is a very simple rule. Y itself is a, so y itself, this guy itself, is a sufficient statistic. Why? Because you can go from y back to lambda y pretty easily. There is a function that brings you from vy, which is y. So we can take our vy to be y, and we can use a certain function u to go back to lambda y, because lambda y is nothing but e to the 2yb over sigma squared. There is such a function that brings us from here to there. So no problem. Okay. So this is a sufficient statistic, and it's quite simple. Okay. So in the special case, okay, in the special case, very special case, in which we are in the special, let's say, maximum likelihood case, maximum likelihood scenario, then our P0 is equal to P1, which implies that eta is equal to 1, which means that the above reduces to y compared to 0. Okay, because ln eta is equal to 0. So the idea here is now the top we declare x hat y equals to b. I just want to write the top. I don't. Of course, the bottom is x hat y equals to minus b. Okay. So in this ML scenario, we're basically looking at comparing y, the observation, to 0. Okay, which makes a lot of intuitive sense when I draw a picture. Okay, so this is our x-axis here. Okay, why does it change? So this is our axis here. Okay, and this is our axis here. All right, and this is minus b, and this is plus b. And so we have two curves here, right? One is the Gaussian centered at b, another is a Gaussian centered at minus b. So the Gaussian centered at b, let's see whether I can draw a beautiful Gaussian. Okay, and this is another side. So this should be symmetrical, if anything. Okay, and over on this side, what color do we like? Maybe this color, right? We have another Gaussian, and I have to draw it in a beautiful way so that we overlap here exactly. Okay, otherwise something is wrong. Okay, and over this side as well. Okay, so this guy here is f of y given x, y given minus b, and over on this side, this is f of y given x, y given plus b. Okay, and this is nothing but the y-axis. So we have these two distributions, and as you can see here, in the maximum likelihood case, we are comparing whether y lies to the right or to the left. Now, when y lies to the right, because I've drawn this in a beautiful way, then the red one is taller than the blue one, right? If we are, if y lands here in the negative part, then this distribution is taller than this distribution because I draw this in a proper way. Okay, so these two should also be of the same height if we draw this properly. Okay, so this is the standard theory of detection for the case of detecting antipolar signals. We can evaluate the probabilities of error. Now I put E0 because the threshold is at 0 and x is equal to 0. Okay, what is this? Now we are making a decision. We are making an erroneous decision when x is equal to 0, when y lies here in this region here. So that this region here is our so-called we make a decision in favor of 1. Okay, And here on the left-hand side, we make a decision in favor of 0. So we call this A0. Okay. So that's nothing but integral over A is A1. A1 here of the density f of y given x, y given the minus b dy. And so here, this quantity here corresponds to x equals to, I should change this to minus b. Okay, then this makes sense. Okay, this is true. Okay, so this is the way we integrate, and I will certainly ask you to do this sort of simple writing down of integrals later on. And this thing can be simplified here. This is not going from 0 to infinity of this Gaussian that is centered at this Gaussian is centered at what? It's centered at minus b. So this is minus b. So this Gaussian is centered at here. We need to write this squared minus over 2 sigma squared dy. Okay. So in this case here, you can use some change of variables and whatsoever. You can write this in terms of the so-called Q function that communications people like, b over sigma. And this Q here is this complementary CDF of a Gaussian, if you wish, minus s squared over 2 ds. Okay, this is called the complementary CDF of a Gaussian, of a if you wish, standard Gaussian. Okay, so the whole point is that this probability of false alarm can be written in terms of b over sigma. Okay, so this b over sigma is an important quantity that we will revisit. I will talk more about it. Now, how about the probability of, this is called misdetection, E0. This is nothing but the integral over A0 of the other density, y given plus b dy. Now, from symmetry, and I'm not going to do it, we have that this is also QB over sigma. All right, well, from the symmetry here. So for this scenario here, for this object here, let's say this object here, what are we integrating? Okay, we are looking at the particular function, the blue function here. You're looking at the blue function, and we're integrating this part here. Okay, we're integrating this. This is very ugly. This one. Say this one. We're integrating this part here. Okay, this small little area here. This is done for this particular guy here. And for the other guy, for the other probability, you're integrating this part here. Okay, so they must be symmetric. This guy here, they must be symmetric, right? Okay. Right, so this has a name. If you study communications and things like that, this has a name. This is called the, what did you call it? So remark, B over sigma is known as the signal to Roy's ratio, I think. Ratio. Okay, so what is B? B is this point, right? B is like something like the power of the signal. The signal is put at B and minus B. So as you can imagine, if I ramp up the signal power, this goes to this side and this goes to this side, and the amount of overlap here gets reduced, right? So if I increase the signal power, the signal to noise ratio is called SNR in electrical engineering. Okay, SNR, if I ramp up the B, then these two curves get pushed further apart and the amount of confusion in the middle gets minimized. All right, so I increase the signal power by increasing B. Now, I can also increase the signal power by making sure that the noise in the environment is small. So if I reduce my noise, then B over sigma, sorry, if I reduce my noise, basically I reduce sigma, okay? Then my signal to noise ratio gets bumped up, all right? So what does it mean for the signal power to be reduced? Basically, now I'm going to transform this curve on the left-hand side to be something much sharper here. So that's the meaning of reduction of variance, right? So as you can imagine, if they are thinner, okay, this guy is thinner, and this guy here is also thinner, then the amount of overlap in the middle is going to be smaller as well. So that's the effect of reducing sigma. Okay, so this is called signal to noise ratio. Now, this Q function as a function of signal to noise ratio looks like this. Okay, this is Q of SNR versus SNR, which is this B over sigma. Okay, how does it look? It looks like this. It's a complementary CDF, so it should have this sort of behavior. Okay. This one cannot go up. It's very difficult to draw this. Last time, before I had to use this iPad, I can draw the board. It will be very beautiful. Okay, and this is half. Okay, so this is the Q function, very important in some aspects of electrical engineering. Communications people like to use this all the time. Okay, I also use this all the time. So Q function looks like this. The higher your signal to noise ratio, the smaller the probability. Okay, so if this gets bumped up, this goes down. So the both probabilities can be controlled. Okay, so now Q function, Q of X has a very nice behavior, and it goes down very rapidly. So it looks like the 1 over square root 2 pi x e to the minus x squared over 2. You don't need to know this, but roughly when x is very large, right, it has this behavior. Well, it has this behavior, so you can see that actually it goes down very fast. And that's a good thing. So if you bump up the signal to noise ratio, your Q function goes down, your probability also goes down. Okay. So in this symmetric case, in this symmetric scenario, the probability of making an error is nothing but half of probability of making an error condition x equals to 0 plus half of the probability of making the same error condition x equals to 1. But these two are the same. They are both Q's, S and R. So this is Q of S and R, where S and R is equal to B over sigma. Okay. So this is the first example that illustrates some aspects of the sufficient statistics and also illustrates how to calculate probabilities of error. So does anyone have any questions here? This is the example concerning detection of antipodal signals in Gaussian noise. This has a name actually. I just remember antipodal signals is something that I learned a long time ago. It's called PAM, I think. Pulse amplitude modulation. PAM. That's QAM also, QAM. So in this case here, y is equal to x plus z, and z is Gaussian noise, and x can only take on two values. So those are its x magnitude is b, okay? But the further apart, the better, easier to distinguish. So these are f of x, these are the distributions, and this is nothing but the likelihood ratio. We haven't taken log yet. We can take log, it becomes more convenient because most distributions are in the exponential family. And it reduces to this particular form where y is compared to a certain threshold. Now, this threshold here, it depends on the prior probabilities. But if the prior probabilities are half-half, then this eta is equal to 1 and this one goes to 0. And in which case here, the rule reduces to something super simple, y compared to 0. And the picture is as follows. We have two distributions, one on the left, one on the right. They are centered at B and minus B. The problem is that there is some overlap here. And this overlap is where we actually make a mistake and we can calculate the probabilities of error exactly. So the point here is that over on this side, we declare x hat of y to be equal to B, and over on this side, we declare x hat of y to be equal to minus B. Okay, just to be clear, right? So we can compute the two probabilities of error in a systematic way. Right? The point here is you need to plug in the correct density, all right? And you need to know where to integrate. So I make this clear here. This from here to here, this is the change of variable integration that I didn't teach you, but you should already know, all right? So we can do this for the probability of, this is called false alarm. And this is called misdetection. Misdetection. Okay, and we see that in this symmetric case, they are the same. All right, and B over sigma is known as the signal to noise ratio in electrical engineering, if you wish, and then they can be computed in this way, and this Q function is very nice. Okay, it comes out in many places. Okay, now let me talk about this maybe halfway through this vector observations before we take a short break. Okay, so now in the previous example we only have scalar observations, or y was scalar, right? So now let us consider a slightly more difficult scenario where we have vector observations. Okay, so we have an underlying phenomenon which is x with some prior probabilities, px1 equals to p1, but our observations are vectors. Our observation is a certain vector y, which is y1 all the way up to yn. Okay, so I put this under bar here to remind myself that it's the as a vector. Then the likelihood ratio test is basically lambda of y, which is this vector, f of y given x, y given 1, over f of y given x, y given 0. Okay, so that is my likelihood ratio, and I'm going to compare to eta, which is equal to p0 over p1. And it should be clear what I'm going to declare here. I'm going to declare 1 here, I'm going to declare 0 here. So the point is that most of the time, our observations y are, maybe I make this capital Y. Our observations are, maybe I would write this as y1 all the way up to yn, are conditionally independent. This is not a bad assumption. Independent of one another, given the hypothesis. So what this is saying is that you are taking repeated measurements. You have a patient that may have cancer, may not have cancer. Instead of taking one blood test, taking blood test once, we take 10 times. All right. And because the same person is IID. All right. So we are taking n independent looks at the phenomenon. So we should be doing better, right? We cannot do any worse because we have more information. Okay. So in this case here, we are conditionally independent. And what we mean here is that for every x belonging to the set of hypotheses, x equals to 0, 1, say the set of hypotheses is 0, 1, then f of y given x can be written as the product of j running from 1 to n of f of yj given x, yj given x. We have this product behavior for every y equals to y1 up to yn. This is Rn. Okay, so we can decouple. We can decouple the hypotheses, the distributions in this particular way. And the likelihood ratio test now becomes lambda y equals to the product over j running from 1 to n of f of yj given x, yj given, okay, what do I want on top? It's better to have 1 on top. And f of yj given x, yj given 0 compared to eta. And on top, we will declare 1. Okay? So here, as I mentioned, it's very difficult sometimes to deal with the case where the densities have not been normalized in some sense. So we prefer to take the log likelihood ratio. This is log likelihood ratio. And in particular, now we can convert the product into a sum. And this becomes log of this guy here, this big guy here. Okay. Usually the log is much nicer to deal with. And then we compare that to, we can write this as equal to sum j running from 1 to n of LLR, there's a log likelihood ratio evaluated at yj compared to log eta. Okay. In addition, so here I've done nothing except to take the logs, okay, and to make use of conditional independence. In addition, if the LLRs, the log likelihood ratios of yj's are conditionally, they are certainly conditionally independent, but say they are additionally conditionally identically distributed. That means all of them have the same distribution. given x, then our life becomes simple because all these guys here, all these functions here have the same form. That is, all the LLRJ dot is equal to LLR dot. So the functions are all the same, and the rule reduces to sum. Okay, so we have n copies here. Okay, sorry. We have sum of j running from 1 to n of log likelihood ratio yj compared to log eta. Okay, so here life becomes very simple, and I want to show you after the break that this really simplifies to something that we can really control. And I think now is a good time to take a break. Here, what we have actually done up to this point is to look at vector observations. And in the case of vector observations, if you assume independence, everything decouples very nicely. And we are looking at a sum of log likelihood ratios of the observations and comparing that to a threshold. Later on, we will simplify this for vector observations of Gaussian channels, if you wish. Okay, so now it's a good time to take a break, and I'll see you back in around, well, we can take it easy and we can come back in 15 minutes time, 35. Okay? Okay, take care. Toilet break. I'm going to pause the recording so people in the room. Okay, so we had a short break and now let us resume. Okay, so today we are not going to talk about very technical things, so hopefully everyone is quite relaxed. All right. So the next example I want to go through is this example of. Oh, by the way, I made this a bit more complete. LRJ, the log likelihood ratio J, is actually this entire quantity here. It refers to this quantity here. So hopefully you're not too confused. Okay, that's the log likelihood. Assuming the observations are conditionally independent but not identically distributed. If they are identically distributed, then all the yj's have the same distribution, in which case we reduce to this quantity that does not depend on j. The observations, of course, will depend on time j, but then the function, the log likelihood function does not depend on j, all right? In the case of IID, all right? Okay, so now let us continue. Let's consider the situation of binary detection of, now we are talking about vector signals in Gaussian noise. All right, it's only a little bit more complicated, but then there is a moral of the story coming up. Okay, so we have a certain source, and the certain source outputs 0 or 1. Okay, now this is a sort of thing that we talk about a lot in communications engineering. Modulator, don't worry what it is, but it basically represents 0 as vector A or 1 as vector B. Okay, then we add on some noise, which is Z vector, which is Z1 all the way up to Zn, and we receive Y vector, and based on Y, we want to design a so-called detector or decoder in order to determine whether the source output 1 or 0, A or B or 1 or 0. 0, so we want to output 0 or 1. And we hope that the detector outputs something, outputs a bit that is the same as what the source emitted, right? So of course, the quality of this system depends on the strength of this modulator, right? If it can separate the 0 and 1 using these vectors very far apart, we expect that the system performs well, right? Suppose the modulator only outputs a certain scalar and not these vectors here. We want to push A to be minus B and B to be B, and we want B to be very big, as we have seen from the scalar example. But now we are allowed to use vectors. So what are the ramifications? Okay, so let us try to take a look. Okay, so before we can continue, let us say that, let us mention that Z is this this basically this vector here. This is an IID random vector with components given by f of z, let's say it has noise variance sigma squared and is 0 mean, z squared over 2 sigma squared. So here z is a real number. And in other words, all the zi's are Gaussian with 0 mean and variance sigma squared. Okay, then it is easy to check, and because these are IID, the log likelihood ratios do not depend on J, and let's say yi is equal to, right? So this A here, this vector A has components A1 all the way up to AN, and the B vector has the same B1 up to Bn. And so when we write down the log likelihood ratio, it will also be a function of these A's and B's. So here we have 1 over square root 2 pi sigma squared e to the minus yj minus bj squared over 2 sigma squared divided by 1 over square root 2 pi sigma squared e to the minus yj minus aj squared over 2 sigma squared. And here we have one more bracket, okay? And one more, not enough space. So after we are all set and done, okay? So this is the, what is this term here? This term represents P of yj conditioned on the source being equal to 1 actually, because 1 is modulated to P, okay? Yj given 1. And this is the situation, the distribution when yj condition x, yj is fixed to 0. Then in this case here, you notice this is at B and this at A. That's the only difference. Now, after a little bit of algebra that I will not go through, all right, this can be simplified to bj minus aj over sigma and into yj minus the other yi. This is yj here. Yj minus bj plus aj over 2 after some algebra. Now, putting all the, so this is for the jth observation. Jth observation is 1 out of n. J is a number from 1 to n. Putting all the observations together, we see that we can form the log likelihood ratio as a function of the y's, y vector, and this is the sum of the log likelihood ratio of the yj, where j runs from 1 to n. And so we have sum running from 1 to j of this guy here. Okay, each one we have already calculated. So we can just copy this down and put this here if we wish. Okay, so we can rewrite this in a nicer vector way, all right, that can expose more dependencies on the geometry of the problem. Okay, so we can rewrite this as b vector minus a vector. You see that if I treat this as Cj, then here what I have is actually C transpose Y, right? C transpose, this is C. If I write this as C, then here is Y. You have a sum of Cj, Yj. This is nothing but C transpose Y. So we can write this as B minus A over sigma, or everything transpose Y minus B plus A over 2. Okay, and we are going to compare this to log eta. Now in this case here, we have transmitted a 1, and in this case we declare we transmitted 0. So this is nothing but bookkeeping and keeping things very careful together. All right. So here what we are making use of is the fact that if we sum Cj, Yj, this is nothing but C transpose Y. Okay. So this is what I'm using, but this is a very simple thing. Hopefully you can take the transition from here to here. Okay. So what is our sufficient statistic? Now look at this very carefully. All right. We can rewrite this in yet another way. Rewrite this as Y transpose B minus A compared to eta prime, which is nothing but sigma squared log eta, plus half B transpose B minus A transpose A. All right, why is this so? This is a matter of bookkeeping. All right. Now, if you have B minus A transpose B plus A, I think this is going to be B transpose B minus, yeah, okay, A transpose A. So this part here, which is equal to B transpose B minus A transpose A, it comes from the multiplication of this and this. And this gets moved over, this part here gets moved over to the right-hand side. So there's some bookkeeping here that I will not belabor the point. Okay? There's some algebra here that I will not talk too much about. But notice the following. Originally, our observation vector y is in R, what do you like? Rn, maybe? No, let's not do n. Yeah, n. Rn. And n could be 1000. It could be really large. But what have we done here? We have simplified the decision rule to this one-dimensional object. This is only one-dimensional. Okay? This is only one-dimensional. Observe that the original vector is possibly very high-dimensional. And it has dimension n. Okay? But we formed a sufficient statistic, which we will talk about in greater detail. So we form a sufficient statistic, which is this guy here, which is only one-dimensional. So the whole idea here is that originally the vector was very high-dimensional, but in order to make the optimal decision in terms of map rule, all we have to do is to take its inner product against B minus A. Okay? And we compare that to a threshold. The inner product between Y and B minus A is a one-dimensional object, is a number. So we have significantly reduced the dimensionality of the problem. Okay? Now, Y transpose B minus A is in fact a sufficient statistic because we can look at this guy and go back to the log likelihood ratio. We can go back to the log likelihood ratio, we can go back all the way to the likelihood ratio. Because I started off with the log likelihood ratio being this guy here. And this guy here I showed is the same as this expression here, or rather this guy here on the left-hand side. So given this guy here, I'm able to reconstruct the log likelihood ratio, which will allow us to reconstruct the likelihood ratio. So the definition of sufficient statistic is satisfied. Okay. All right. So now, in particular, in the ML setting, where the probabilities are identical, the prior probabilities are identical, this rule becomes y minus b, y transpose b minus a, and very soon I'll drop all these things below. Okay, compare it to half. This is norm b squared minus norm a squared. Okay, and we make the decision in favor of one above. Okay, so let me remark that the test involves observations only through its inner product, only through its inner product with B minus A. Okay, so this means that Y transpose B minus A is a sufficient statistic for our binary hypothesis test in this case here. So this is very economical, all right? Because all we care about is this particular direction. Every other direction does not really matter, okay? So we have the geometry of the problem is as follows. So in high dimensional space, you got A, B here, and you connect A and B. I want to connect it properly. To connect A and B, and this is perhaps their midpoint, right? And from the midpoint, you can draw this perpendicular bisector if you wish. Okay, so this point here is A plus B over 2. All right. So we can rewrite actually the test as, okay, so this is a set of all points, this perpendicular bisector is a set of all points y such that B minus A transpose over 2, y minus B plus A over 2 equals to 0. Okay, so why is this so? Okay, we don't actually need a 2 here. We don't have to have a 2 here. So if we have this line that I have just drawn satisfies this relationship. Why? This point is A plus B over 2. So this part here, suppose this is our y. All right. Then what happens here is that this part here is equal to this. Okay. What we are saying is that this vector here that I've just highlighted, this vector here is perpendicular to this particular line here. That explains this set here. Understand? Not too difficult, right? So the whole idea is that y should be projected onto this B minus A, okay, in this particular way. So in another way of saying it is the following fact. The two hypotheses can be distinguished by the component or the projection, if you wish, of the observed vector y in the direction of the signal vector which is B minus A. Okay. In other words, the projection is a sufficient statistic. This is the projection onto B minus A. This is the projection, is a sufficient statistic for the binary hypothesis test. Okay. So we have basically reduced the problem back down to a one-dimensional problem. Okay. Originally, the problem was high-dimensional. Why? But we have reduced the problem to a one-dimensional problem. Now let me draw the situation where A is equal to the 0 vector. Okay. Then we have this scenario here. So B is here, for example, and A is here. Okay. And I can draw this line here. I can draw this particular line here, and this is my B. Okay. And this is Y. Maybe this is B, okay, but this is Y here. So I'm looking for the projection of Y onto this. All right. And this part here, this segment here is nothing but B minus A, well, A is equal to 0, never mind, transpose Y over norm of B minus A, B minus A. Okay, in the general case. Now this is too small to be seen, right? So let me blow it up a little. This vector here is B, in the general case, B minus A transpose Y. So that is the length, okay, times B minus A, right? So in this case here, no matter how high dimensional B is, Y is somewhere here. In order to make the best decision, we project Y onto this subspace here, project Y onto this subspace, and then we just look along this subspace to see whether Y is closer to B or Y is closer to A. So that's the projection. Let's call the projection this P here. Okay, this P is this vector here. And then we can assess on this particular subspace, everything is one-dimensional. Okay, then this reduces to our simple binary Gaussian problem that I talked about just now, one-dimensional. We are in this land here, one-dimensional land. And then we can do exactly the same operations as we did for the one-dimensional case. Okay, so this is a matter of geometry and projection. Hopefully this is clear. So we can also rewrite the decision equation above as LLR, which is a log likelihood ratio, taking in Y, as B minus A over sigma squared into B minus A transpose Y over B minus A minus B minus A transpose B plus A. This is just a matter of bookkeeping. And compare it to log eta. Okay, so this is nothing but the component of y in the signal direction. All right, the component of y in the signal direction. And so this is this length here. This is nothing but this. Okay, we are projecting y onto this particular subspace. Here I draw a equals to 0 for ease of notation. Okay, so the problem reduces to the one-dimensional. The problem reduces to the one-dimensional case. Because now all the action happens here, and I'm assessing in this one straight line here whether P is closer to B or is it closer to A, and then I can calculate my error probabilities. Okay, so in order to do so, in order to calculate my error probabilities, let me again make a simplified assumption where A is equal to minus B. So we have some symmetry, and we don't have to work with too many symbols. Then the log likelihood ratio y, this is a vector, is equal to B over sigma squared 2B transpose y over B. This is minus 0 because B plus A is equal to 0. Since I take this, I consider this scenario. I don't want to consider too many things. The book considers this in a more general fashion. Okay, so if in this case I take A to be equal to minus B, then this guy here vanishes. I don't want to deal with this, and all these can get simplified as well. Okay, so the decision gets reduced to 2B transpose y over sigma squared compared to log eta. And you notice that this is very similar to the one-dimensional case. The only difference here is that these are vectors now, but after the projection, we still get a one-dimensional problem, right? So all we need to do is to work in this particular dimension, work in this particular subspace. Okay, and then we can compute, for example, the probability of error given x is equal to minus b, and now b is a vector. And through the same type of calculation as we did for the one-dimensional case, you will notice that this is log eta over 2 gamma. All right, gamma has not been defined, and probability of E eta given x equals to b is equal to q of minus log eta over 2 gamma. Here, gamma is a proxy of the signal to noise ratio, which is given by b over sigma. Okay, and I'll derive these two in a short moment. I'll derive these two very quickly. Okay, so let me go through, before I calculate this, let me go through this example one more time. Okay, so now we want to do the problem of binary detection of vector signals in Gaussian noise. And the whole idea is as follows. This is very important because we would like to transmit a bit reliably. A bit is basically 0 or 1. And this is going to get modulated onto vectors A or B. Actually, more generally, you can modulate 0 or 1 onto functions. Okay. Then this A or B gets corrupted in Gaussian noise. All right, and you receive Y. All right. So if you based on Y, we want to tell whether the source emitted 0 or 1 over here. Now this Z, however, is going to disrupt our system because it is Gaussian noise. So we can form the log likelihood ratio as follows. Okay, this is only for the J component. So the J component looks like this, but it's very simple because all the components look the same. So we can put all the observations together here. And we notice through a little bit of linear algebra and remembering what is inner product, that this log likelihood ratio can be written as follows. Okay, so the point here is that originally the Y vector could be very high dimensional, but in order to make an optimal decision, we have to take the inner product of Y in the particular signal direction. All other directions orthogonal to the signal have got no use whatsoever. Okay, and this is a matter of rearrangement. And the remark is that originally our observation vector could be possibly very high dimensional. However, we formed a sufficient statistic Y transpose B minus A, which is only one dimensional. Now, note that sufficient statistics need not be unique, okay? There could be multiple sufficient statistics. This is only one of them. Now, in the maximum likelihood setting, we can get rid of this particular term because eta is equal to 1. and we recover this. All right, and the picture is as follows. So here is A, and here is B, and this is their perpendicular bisector. Okay, so this perpendicular bisector can be represented by this set here. All right, and what we want to do is to consider for any particular Y here, for any particular observation, project onto this, and then look in this direction as to whether the projection, this projection here, is closer to B or closer to A. Now, if it so happens and you're so unlucky that it ends up in the middle, then you cannot make any reliable decision. But say it is somewhere here, you project onto here, then of course, in the maximum likelihood case, you will declare A, you won't declare B. Okay, suppose it's over here. Hang on. Suppose it's over here, we project onto here, then this is our projection, it is closer to B. Okay, so the whole idea is we always have to project onto this signal direction. Okay, so here is yet another picture when A is equal to 0, when I can show you a little bit more about the projection. So here is Y, any particular observation is a particular vector, and you're projecting it onto this signal direction. And this is the equation of this projection here. Okay, we are looking for the distance multiplied by the particular vector. So the decision equation can be written in this form here. And now let us consider the special case in which we are antipodal. Then the problem even simplifies because we can get rid of this, and the log likelihood reduces to the following. And you notice that now we basically look as though we are in the original scalar scenario, because here these two are vectors, but then I'm forming a single scalar B transpose Y and comparing that to a certain scalar which is log eta. So B transpose Y, we are comparing that to this after multiplying with a few constants. Okay, and now I want to show you these two things. I want to show you how to calculate these two. Okay, so let us see whether we can calculate this. Okay, now I'm not sure whether these are in the correct direction, but we can show it from first principles. Okay, let us compute this guy here, and let me show you through some integration that we can get this cube. All right. So consider, so this sort of calculation I may ask in the exam because it's simple enough. X equals to minus B. Okay, what am I trying to do here? Okay, so this is equal to what, and what are we integrating? Well, the ground truth is that we don't have tensor. So Y here, condition on X being equal to minus B, we are integrating over dy. Right, this is the ground truth, this is the distribution. Okay, this is the distribution of interest because we are conditioning on this guy here, so we are taking X to be this guy. Can you see? Okay, so another major consideration is what we are integrating over here. All right, so we are making an error, right? So we want to make a decision in favor, in this case we are making a decision in favor of plus B, because now we are conditioning on minus B and we are error. Okay, now I should have written that this one is 1 here. Okay, 1 corresponds to plus B. So we are integrating over the region 2B transpose Y over sigma squared greater than log eta. Okay, so this is the exact integral expression. Okay, so let's try to simplify this a little bit. Under X equals to minus B, okay, we have that Y is distributed as minus B sigma squared IM. Okay, so this is the mean, and this is the covariance matrix of Y. Then what is B transpose Y? Okay, distributed against. So this is minus B transpose B, if you wish, and B squared sigma squared. So this is a method of transformation of Gaussian random variables. Okay, so you have to be quite familiar with this. We can write this as get rid of this first. Okay, norm B squared like that. Okay, so if you have a Gaussian random vector that is distributed according to this, and you take the inner product, the mean gets scaled, and the covariance gets multiplied by B squared like this. Okay. So now let's take the plunge and let's compute this probability. So let's move this down here. You're computing this. So this is integral over what? Now, B transpose Y Now B transpose Y is our variable of interest, and B transpose Y has this distribution. Okay, so now this becomes 2. I'm replacing B transpose Y by Z sigma squared greater than log eta 1 over square root 2 pi norm B squared sigma squared. So that is the covariance. This part is the variance of B transpose Y. I got it from here. Okay, and the rest I'm going to copy down e to the minus z plus norm B squared. This is where the mean came from. The mean here is minus B. So I'm copying this down. This is the mean here. I'm copying this down here. Okay, and we need to square this, and we need to divide by the proper variance, or this. Here's the variance. Okay, dz. Now we have converted this very big dimensional integral of n objects and variables into just scalar integration. Okay, because I found this new relationship. Okay, so now I am not going to do this integration and change of variables, but you can take, say, how do we take? We are going to take, say, w equals to, I'm going to get this wrong if I write this, maybe z plus norm B squared divided by norm B sigma, something like that. We change this variable in this particular way, and then we will see that this is going to be q of log eta over 2 gamma plus gamma. Gamma equals to norm B over sigma. Okay, so I'm not sure about this expression here. I'm not sure about this. Let's just erase this for now. But this thing that I've done below is the correct calculation. All right, this is the correct calculation that was also done in the book. So let's just ignore the thing about, I'm not sure about that. But this, as you can see here, basically what we have done is the following. If x is equal to minus p, then y is equal to x. Remember, y is equal to x plus z, right? So the mean gets shifted from the z mean to minus p, and z has covariance matrix given by sigma squared I, because it is independent across time, and each component is Gaussian with mean sigma squared. So we have this situation, this covariance matrix here. Then we can take B transpose Y. You basically take B transpose of this guy here to get this, and B transpose of this particular covariance matrix recovers this. So this is the same as variance of 5y is equal to 25 to variance y. We have to take square here, right? So there is a small little result that we have to take the norm of B here. Okay, then we put this particular distribution inside here, and then we basically do some change of variable here, but carefully to get this sort of error probability behavior. And this is now the effective SNR, signal to noise ratio, in the multi-dimensional case. Okay, so that's one calculation for this is the probability of false alarm. You can do the probability of misdetection on your own or look at the book. Okay, the point here is that we derive a new distribution, scalar distribution. All right, this is scalar. And then we can work in the scalar case, because working in the vector case is a big headache. All right, but the intuition here is that when you form the sufficient statistic, you are basically projecting y onto the signal dimension and looking at, where's my picture, and looking at y's behavior in this signal dimension, and all the action happens there. It reduces to the scalar case, as what I have done here. Okay, any questions on this calculation? Here, so this is equal to, I'm sure this is correct because I just did, I'm not sure what I put. So my notes, my handwritten notes may not be completely correct, but this handwritten notes is most likely completely correct. All right, and here you can derive this and go and check this. Okay. Any questions? So in the maximum likelihood setting, maximum likelihood, then this one goes away to 0, and we recover this, which is corresponds to the scalar case, where this is the SNR. Okay, it makes it is analogous to the scalar setting. You can see, right? This analogous completely to the scalar setting B over sigma. Because in the scalar setting, this B is basically a scalar. We don't have to put the norms anymore, and we recover B over sigma, which is the SNR in the scalar case. Okay. Now let's do yet another example to illustrate the point of sufficient statistics. By this time, you may have forgotten about Poisson process. So let me remind you about Poisson process. Now, let's see another example. Now I have got two Poisson processes, and they have two different rates. So in the case X, in the null hypothesis, X equals to 0 corresponds to the Poisson process having rate lambda 0. And in the case of X equals to 1, this corresponds to our Poisson process having rate lambda 1. And lambda 0 is not the same as lambda 1, otherwise there's nothing to do. Okay, so we are going to observe a Poisson process up to time t, and we want to make a decision as to whether the Poisson process has rate lambda 0 or lambda 1. We want to guess. So what do we have? We have observations, which are y1 all the way up to yn. And the y's here are analogous to the SIs that we have studied. So what are these SIs called? Arrival epochs. Remember arrival epochs, when the goals are scored. I cannot spell arrival. Arrival epochs. Here I use Y because in this topic we use Y. All right. In Poisson process we use S, but you should know that these are arrival epochs. So I observe these arrival epochs. Okay. Sorry, I just said the wrong thing. These are basically the inter-arrival times. It's analogous to the XIs. They are the inter-arrival times. Okay, so these are IID, inter-arrival times. Doesn't really matter what I talk about because all these stochastic processes can be moved from one domain to another, no problem, right? So we observe these IID inter-arrival times, and we can form the likelihood f of y given x, when x is lambda 0 or lambda 1, say lambda L. Okay, L is in 0 or 1. Okay. So this is what this is equal to, because we are IID, this is some product of lambda L e to the minus lambda L yj. Here yj all non-negative. Okay, does that make sense? Yeah. So L indexes the hypothesis. Okay, this is lambda j is either lambda 0 or lambda 1. So this is nothing but an exponential distribution of rate lambda L. Okay, so we want to see what the optimal decision looks like. So let's form the LLR, log likelihood ratio of y. Okay, so now we take the log. My ln and my log are the same. Okay, of f of y given x, y given lambda 1 over f of y given x, y given lambda 0. Okay, so let's do this slowly. This is log of product j running from 1 to n of lambda 1 e to the minus lambda 1 yj over lambda 0 e to the minus lambda 0 yj. So as I said, a lot of distributions are exponential families. All right. So here it's convenient to take the log because the log and the e will hopefully cancel away nicely. Right. So after you're all said and done, and I've done enough algebra here, this is equal to n log lambda 1 over lambda 0 plus sum j running from 1 to n of lambda 0 minus lambda 1 of yj. Okay, this needs to be flipped because of the minus sign here. So this is the log likelihood ratio, and the map test corresponds to n log lambda 1 over lambda 0 plus this constant here, lambda 0 over lambda 1, sum of yj up to n. Compare that to log of eta. All right. So this is nothing but our map test. And what do you notice? Now, you can have observed 1,000 inter-arrival times. All right. You have observed 1,000 goals. All right. And you want to infer what is lambda 0. You want to infer whether lambda is lambda 0 or lambda 1. Now, the story here in this expression is that you don't need to observe your 1,000 inter-arrival times. You just have to observe their sum. And their sum has a certain name, Sn. Right? The nth arrival epoch is sufficient for you to make the optimal decision. You don't have to see where all the goals arrive. You just have to see by this particular time, all right, how many arrivals do I have? All right. So the punchline here is that Sn, I meant to use this black. Sn equals to sum up to j of yj is a sufficient statistic of this binary hypothesis test. Okay, because the log likelihood ratio test or the likelihood ratio test, maybe I do this, likelihood ratio test depends only on Sn, the nth arrival epoch. It doesn't matter what happens before the nth arrival epoch. I don't need to know that in order to find out what is lambda, whether lambda is lambda 0 or lambda 1. All the stuff before the nth arrival epoch is irrelevant. Okay, so Sn is a sufficient statistic for this binary hypothesis testing problem. Okay, why is this intuitively true? Okay, this is true because Sn, this is intuitively true because the first n-1 arrivals are uniform, conditioned on the nth arrival time. Okay, so there's no information in the first n-1 arrivals anyway. Okay, there's no information. So here we are interested in distinguishing between Poisson process with rate lambda 1 or rate lambda 0. And we make a sequence of observations which are the inter-arrival times. Yi equals to, we used to call it xi. So we are able to form the distributions here by recalling that inter-arrival times are exponential lambda. Okay? And we are able to form this log likelihood ratio here. After some simplification, we get this expression here. And what do we see here? We see that this constant can be brought outside. And we are only going to look at the sum here and comparing some simple function of the sum to this threshold. And we can see that all that matters for us to make the optimal decision is Sn, nth arrival epoch. Everything that happens before is not important. Now, I want you to think, because I have set a certain beautiful question, okay, that in this particular scenario, please remember this problem, okay? So I say this for a reason. Please remember this problem, because I like Poisson processes, and every day I do hypothesis testing. All right. Please remember this problem, and in particular, think about some slight variations. All right, here you see, here all these two are Poisson processes. What if one of them is not a Poisson process? Suppose let's think of a particular scenario. Okay, so we have some arrivals. All right, so this is our timeline. Okay, this is our timeline. This is 0, and these are some arrivals, some close, some far. Okay, so this is some basically this is S1, S2, S3, S4, S5. Okay, we make this observation, and then what we want to do is to decide something. Okay, but suppose, for instance, now my inter-arrival times are the following. Inter-arrival times under hypothesis 0 is that inter-arrival times is following exponential lambda, and under hypothesis 1, inter-arrival times follows a Erlang, slightly different, lambda of order 2. So what is the story here for this hypothesis test? All right. So usually customers walk into my shop according to a Poisson process. That is the normal scenario. That's the null hypothesis H0. Okay. What is the story I want to come up with? So under H1, right? Someone else. So this is my shop here. This is my shop. So I'm inside here, and customers walk into here. They form a Poisson process and walk into my shop. But then I have some adversary here. All right, that tells every second customer, all right, to walk not into my shop, but to channel every second person to come into my shop to go to McDonald's instead. So my shop is selling something, but there is some adversary who says, okay, every person who comes in, I let every other person to go in. I let the first person go in. I let the third person go in. I let the fifth person go in. So what I observe in my shop, because I do not know that there's an adversary outside, is that I observe this process, this arrival process. Okay, then the second and the fourth person gets siphoned off into my competitor. So I want to know whether actually this happens or not. So what is a sufficient statistic? All right, so in this case here, life is not so simple, right? Because we have an Erlang distribution and an exponential distribution. So I'm not sure what is a good sufficient statistic and whether a sufficient statistic can be so simple as Sn, right? Because now the alternative process, right? This is an alternative process here. It's no longer memoryless. So life becomes interesting. Okay, so I can come up with this story. This is a beautiful story, right? Yeah. Anyway, yeah. So this is not so simple anymore, right? There's no slight variation. All right. Anyway, this is my shop. Okay. So there are many things that we can play with. There are many models that we can play with. But before we do that, I want to talk about, in the remaining time, I'll talk about sufficient statistics a little bit more. So we informally introduce it, we formally introduce it, but we didn't talk too much about it. So let me talk a little bit about sufficient statistics now. Okay. So the objective is to seek equivalent representations, equivalent characterizations of sufficient statistics. Okay. So here's a theorem. We already know what is a sufficient statistic. Recall that V of y is a sufficient statistic for the binary hypothesis testing problem if there exists a function u of v such that I can recover the likelihood ratio from V of y. Okay, this is basically our recollection. All right. So basically I can go backwards. Okay. So for example, for the vanilla Poisson process problem, my y could be my vector of observations, my vector of inter-arrival times y1, yn, and my v of y, which is my presumed sufficient statistics, could be just a sum. Okay. Now the question is whether I can get back to lambda of y, and yes, I can, because the lambda of y is nothing but this simple function here. Okay, and it only involves this linear function of my sum, my Sn. Okay. So in this case here, this is basically Sn can be easily seen to be a sufficient statistic for the Poisson process binary hypothesis test. Okay. So what are some equivalent characterizations of sufficient statistics? Okay, theorem. Let V be equal to Vy, be a certain function, be a function of y for a binary hypothesis test. So this Fn is a function, right? The following are equivalent, and we will prove this following are equivalent. Okay, so number one. So this is the standard definition, right? A function u, there exists a function u such that we can recover the likelihood ratio from V. Okay, so this is the definition. There's nothing serious. I already recalled the definition for you. Two, so these are all equivalent. For any priors, P0, P1 bigger than 0, okay, the posterior probability satisfy P of x given y, x given y equals to P of x given v, x given vy. Okay, so by the way, this theorem is only for the discrete case, discrete y case, okay, because there are some issues with the continuous y case. So what this is saying is that, okay, if you look at this, you will see that another way of saying this, and I'll put it at the side, is that x, v, y forms a Markov chain. Okay, in this order. All right. So what is the problem is that here, okay, now note that x, y, v always forms a Markov chain. Always, because v is a function of y, always forms a Markov chain. So the non-trivial statement here is that x, v, y forms a Markov chain. The v is in the middle, all right? So what this is saying is that the relation between x and y is xy, okay? But in order for me to learn about x, it suffices for me to look at a function of y. I don't have to look at the whole y. There's a lot of information. But looking at this function of y can tell me as much as I want about x. Okay? So there is no loss of information. All right? So in particular, right? So in particular, if you know information theory, this is mutual information. There's some relationship between x and y. And the relationship does not get destroyed if I look at x and v. The mutual information gets preserved. Okay, this information theory. This one is in section 2.9 of Kober and Thomas, the standard information theory book. Okay, so basically this says that, remark, V contains basically sufficient information about x in comparison compared to y. Y contains a lot of information. It's an observation. But even if I process the observation by a deterministic function v, I still have the same amount of information to say something about x. Okay? So the final characterization is the following. So the likelihood ratio of y is the same as that of vy. Vy. So in other words, lambda of y is equal to pv given x, vy given 1 over pv given x, vy given 0. So notice that originally the likelihood ratio was defined as py given x, y given 1 over py given x, y given 0. So the non-trivial part of this statement is that I can change the y to v. All right. So here was y, I can change to v. Okay. Basically, I can rewrite this. So these three statements are equivalent, and we will go. And the reason why we want to prove this is because we want to familiarize ourselves with the notion of sufficient statistics. Actually, the best notion of sufficient statistics to me, because I'm an information theorist, is this. But I have not introduced what is neutral information to you. So I cannot really use that characterization. Okay. So proof. Okay. So we are going to prove things in this order. 1 implies 2, implies 3, implies 1. Then everything is proved. Okay. So now 1 implies 2. Okay. So what is 1 implies 2? There exists a function u so that this holds true. Implies this Markov chain. Okay. So we're going to prove this way. 1 implies 2. Okay. So let us see. So now let us form this particular function p of x given y, 0 given y. We are only interested in the binary hypothesis testing scenario, and this is a matter of base rule. Y given 0 over p0, p of y given x, y given 0, plus p1, p of y given x, y given 1. Okay, this is nothing but base rule. Okay, so now we can divide the top and bottom by this p1, p of y given x, y given 1 over p of y given x, y given 0. We're just dividing, right? No harm, right? So this is equal to, we can rewrite this as p0 over p0 plus p1 lambda y. Okay, and we can rewrite this because we know of the existence of u as p0 plus p1 uvy. That is, and here we are making use of 1. Okay. So the idea here is that now what have we done? We have asserted that p of x given y, 0 given y, this is the conditional probability of x being equal to 0 given y equals to y, is a function of y only through the sufficient statistic Vy. Okay, it's a function of y only through Vy. At least let's see what we have to prove. Okay, so basically what we have shown is in fact this as well. Okay, so what we wanted to show is this. We wanted to show this. Okay, and what we have shown is this above thing. So what it's saying is that p of x given y, 0 given y, is a function of y only through v of y. And of course, the same is true for p of x given y, 1 given y, by symmetry. Okay, so we can basically rewrite this guy here, which is this guy here when x is equal to 0, as x given vy, because we have already made this statement, is a function of y only through vy. So this guy here, which is this, is equal to this guy here because this object is only a function of y through vy. And so we have proved this. And you see in this proof where P0, P1 positive is important. All right, because if this is not equal to 0, not greater than 0, then something bad would happen here because this we cannot be able to, some things here will be equal to 0. For example, this guy here will be equal to 0, then things are not so meaningful anymore, I feel, right? So if P1 here is equal to say 0, then this whole thing cancels, and we don't expose the dependence on Vy here, right? So this P0, P1 is quite important. Okay, so now let's go from 2 to 3. That's the next proof. Okay, so we have this relationship here, and we want to show that the likelihood is the same as that of Vy. So this is a matter of careful calculation. So look at this. So this is the next proof, next part. Okay, so we have P of 2 trying to imply the 3. P of x given y, 1 given y over P of x given y, 0 given y. So we are making use of part 2. P of x given v, 1 given vy over P of x given v, 0 given vy. Okay? So that's it. So now we can apply Bayes' rule multiple times to the following calculation. Okay? This is P of y given x, y given 1. We are going to apply Bayes' rule 4 times. Okay? To each one of the terms here, 1, 2, 3, and 4. And we see a lot of things will be cancelling. So let's apply Bayes' rule to this guy here. Okay, so this is equal to this multiplied by px1 divided by pyy. And here we have p of y given x, y given 0, px of 0 over pyy. Over on this side here, we have p of v given x, vy given 1, p of x1 divided by p vy. And here we have p of v given x, vy given 0, p of x 0 over p of v vy. Okay, so what have we done here? We have written out a lot of things, but we have managed to cancel a lot as well. So this cancels this cancels over here, this cancels this, and this cancels this. And so what can we see here? Finally, this guy here is equal to our lambda y. And here over on this side here, we have p of v given x, vy given 1 over p of v given x, vy given 0. So now what we have seen here is that the likelihood ratio, which is this guy here, is nothing but the likelihood ratio of y, which is the left hand side, is the likelihood ratio of vy. Okay, so this is a matter of applying Bayes' rule 4 times carefully and cancelling things properly. And why here is it important for the priors to be positive? Because we are cancelling. All right, we cannot cancel 0 by 0. Okay, so this is 2 implies 3, and this is done. 2 implies 3. Okay, finally we do 3 implies 1. Okay, so what is 3 and what is 1? So 3 is basically that the likelihood ratio is the likelihood ratio of y is the likelihood ratio of vy. Okay, so note that, and this is, let's start here. The right hand side of equation star is a function of y only through vy, the sufficient statistic, through vy, a function of y. Therefore, one says that vy is a sufficient statistic of the binary hypothesis. That's if I can find a u so that I can go backwards. So here is the u that I will choose. U dot is equal to p of b given x dot given 1 over p of b given x dot given 0. Well, if you're not comfortable with dot, u of v is equal to, I choose it this way, v given 1 over p of b given x, b given 0. And if you are still not comfortable, you can replace the v here with vy. Okay, and this actually shows part 1. Okay, because we have demonstrated the existence of this u, okay, that allows us to go backwards. From basically it allows us to go backwards from the v to the likelihood ratio. Okay, we have demonstrated this u here. So this all these 3 proofs here allow us to show that allow us different characterizations of the sufficient statistic. Okay, so maybe let me go through this a little bit more, one more time, and hopefully this will be clear. Okay, the proof is not so important, the statement is more important. Okay, So the standard way that we define sufficient statistic is through this relationship. We say that Vy is a sufficient statistic of y if I can find a function u such that I apply u to v, I recover the likelihood ratio. And the likelihood ratio is super important for making optimal decisions. Now, another way of saying this is that this remark here. V contains sufficient information about x compared to y. So whatever information y can tell me about the hypothesis x, v can tell me the same information. So mutual information is preserved. Another way of saying it. Okay. The third way is that the likelihood ratio of y is the same as that of Vy. Okay. So that is the likelihood ratio of y here. And it can be the same as the likelihood ratio of Vy. Okay, so V is some compressed observation, you can think of it. Y is some very large vector. You compress it down to a scalar, like what we did for the vector observations case. And thus, by looking at this scalar, I can form a log likelihood ratio or likelihood ratio that does just as well as if I looked at the big vector Y. Okay, so that is the implication here. I will not go through the proofs because the proofs are just algebra. I've already gone through the proof just now. Okay, so this actually ends our discussion on the sufficient statistics. And what we have done up to now is really called Bayesian hypothesis testing. Okay, because there are priors on the underlying hypothesis X. Someone said that this person here has a 5% chance of having cancer, even before obtaining any observations about the person. Okay. But who says that the person has a 5% chance of having cancer? That's a very bad assumption. So we should adopt the Neyman-Pearson setting. Actually, I prefer the Neyman-Pearson setting. Okay, so in the remaining few minutes that I have, I will not take up all your time. I will briefly discuss the Neyman-Pearson setting. Neyman-Pearson rule, if you wish. Okay, so here we do not need to assign priors to the events x equals to 0, x equals to 1, because this seems rather artificial. Okay, we can define two error probabilities PMA and PD. Okay, this is the probability that y belongs to D, condition of x equals to 0, and y belongs to D means that the decision is made in favor of x equals to 1. Okay, so y equals to y in D, this is called the decision region in favor of hypothesis 1. So here I made a mistake because the underlying hypothesis is 0 and I said that it's 1. It's called false alarm. All right, and we can define P misdetection as probability y in D complement given x is equal to 1. By the way, this sort of things are also called type 1 error. Type 1 error is not so serious. We control it by epsilon most of the time. This is called type 2 error in statistics. Okay, so in the Neyman-Pearson setting, right? How do we control these two guys? There are no prior probabilities on these because we don't want to assume that there are prior probabilities on these events. Now, suppose I don't want any false alarm. Okay, I don't want any false alarm saying that, okay, this person does not have COVID, but I say he has COVID and I haven't quarantined him. What do? I do not want any false alarm. Just say that everyone does not have COVID, right? But is that very wise? No, right? Because these infected people will walk around. So the point I want to make is the following. It is always possible to make a probability of false alarm equals to 0. Right? So this is our objective, right? One of our objectives. We have two objectives here. We're going to make these two very small. Right? We're going to make these two very small. But if you have studied optimization, right? We like to make one thing small. When we are faced with two things that we want to make small, then we have a headache. because we cannot have two objective functions. Don't know how to deal with that. We can have one objective function that we try to use variety of optimization algorithms to make small. But if we have two things, then we have a headache because we cannot make two things small simultaneously. So here I've made one thing small, just by declaring that everyone does not have COVID. Everyone can walk around. All right. So what do I mean by PFA equals to 0? I mean that we will take D equals to empty set. Well, if D equals to empty set, then this guy here is the empty event here, and this probability is 0. So I will never ever make a decision in favor of x equals 1. Never decide x equals to 1. Always decide x equals to 0. But is that very wise? No, right? Then all these infected people walk around in your community. So this is not very wise, because probability of misdetection is how much? In this case here, is equal to 1. Do you want that to happen? Because now if D is empty set, then D complement is a full set, right? The probability of full set is equal to 1, right? So that is not very wise, right? Because you don't want to always miss. Here you are saying always miss. So this is very bad, right? So what is more meaningful? It is more meaningful to understand the trade-off, and this is the key word that we will emphasize next time. The trade-off between the two probabilities, two error probabilities. Okay, so we want to understand the trade-off. Suppose, and the whole idea here is the following. Suppose I can tolerate probability of false alarm epsilon. Epsilon is 5%. What is the best probability of misdetection? Smallest probability of misdetection. So that is the formulation for Neyman-Pearson. All right, we don't have any priors on anything, but I can tell you that I can tolerate 5% false alarm. That means we go to this 5% of the people we wrongly quarantine them. Don't care. All right. So the idea here, let me make it clear. We minimize probability MD subject to probability of false alarm less than epsilon for some epsilon small. This is the formulation that we will consider. Okay, so now we will abbreviate the error probabilities as Q0A. So we are going to change notation slightly. Probability Y in A or D doesn't really matter. X equals to 0. And Q1A equals to probability Y in A complement. So the A is D, okay, sorry. Condition X equals to 1. So this is Q0, Q1. All right. So A represents some decision region in favor of X equals to 1. Okay, A or D, doesn't matter. Okay, so we are interested in also threshold tests in this case, threshold tests, such that A looks like the following. Okay, all the Y's such that the likelihood of Y given 1 over Y given X, Y given 0 is greater than eta. So this is in favor of X equals to 1. If Y lands inside the set, then we declare that hypothesis 1 is true. So we have seen that this sort of set is very useful for the Bayesian setting. All right, essentially, in the Bayesian setting map rule, we make use of this log likelihood ratio or likelihood ratio. We compare that to a threshold, and we saw the very first proof that we did that the map decision is actually optimal. Now we change our problem into this constraint optimization problem. Do you think that this A rule is optimal in any sense? This will be the subject of what we talk about next time. Okay, so I just want to give you a start. Next time I'll repeat this last part, and then I will show some interesting theorem concerning the optimality of this threshold test for the Neyman-Pearson setting, which is this particular setting. So Neyman-Pearson is non-Bayesian, right? Because we don't have priors on X. So this is where I will stop today. And I wish you a very good weekend. And next week, we cannot gather here because it's Good Friday, but I will do recording over Zoom. Okay, so everyone can still attend either during the lecture time or at your own leisure. I can do recording, and then of course the material is examinable. Okay, so thank you very much for your kind attention, and I wish you a very good weekend. Okay. No. So that is a special case of the last example for Gaussian. In the general case, PFA and TMB are not the same. Okay. Yeah. In a very, very symmetric example, they are the same. So where was I? Okay, have a nice weekend and submit the homework. I have not created the next homework yet. So I'll go to my office to create it now. Okay, 再见. Good night. Bye-bye. Where's my mask? Bye, take care.